Okay, so basics of getting your snakes installed, like don't bother with going to the official website and all of that stuff. I made it quite easy. So if you go to the GitHub repository, which we provided inside of the exercise sheet, basically installing everything is done using pipenv and all the requirements that you need. So I recommend you first cut here, you clone the repository on your system. Then you basically, there's a very simple way to install the dependencies. You just do pipenv, you run the command to install all of these dependencies, basically. If you don't want to use pipenv on any of these things, you don't have to. Just make sure that you install all of these Python dependencies that are in the pip file. Essentially nothing else really matters. You don't really have to use the pip file, but it's just there for your convenience. You just install it and then you activate basically getting into the environment if you're using pipenv. And basically then what you have is a working environment in which we have, for example, the CPN that does the reading and writing to the file. So I think it's just 67 lines. Well, most of the stuff is essentially just here. There isn't really like a lot of, it's just a lot of declaring, okay, this is a place, this is a transition. I will go into more details there. Another thing that is provided with this repository is like a tiny, like few files of a library that basically allows you to do like simulation that is a bit similar to how CPN tools does simulations. So basically, you have basically this tiny helper functions. So if you want to run like one step of the PetriNet where basically it just will find all the transitions that are currently enabled and applicable in your current model state and basically selects a random one and then fires it. And then it just tells you, okay, which transition it just fired. That's basically all it does. And then the second one is the same thing, but basically if you want to run the simulation continuously until you have no more transitions that are enabled, basically it just runs it over and over. And that's it. It basically has a limit so that you don't have like an infinite loop. And then it just draws every single result into a PNG file. So basically the state of the CPN, which is basically how the tokens and all of the transitions and the places and how they look in a graphical manner similar to CPN tools is what this also does. So if you do the run simulation with the library, you will also get something like this where it's generating the PetriNet graph for whatever PetriNet that you have put into this file. Now that we know a little bit about installing Snake CPN and how the exercise library is generally structured, this is a tiny tutorial and instructional video for mainly the first exercise, and also it's a tiny explainer video on how generally you go about making a PetriNet model in snakes. So as I explained before, importing the simulator library is optional, but it makes it a bit easier for just running the simulation once you have a CPN model. And generally the structure for creating a PetriNet, well, basically you create places, and usually places are given a certain name. For example, here, the place on the top here is called file system. And you can initialize this place with a set number of tokens. This is provided in a list. And this, in this case, only contains one token, which is how we're representing a file here. In this case, it's just a tuple. So we are not actually going to do more complicated things like putting file restrictions or permissions, and so on and so forth. We're just going to put like a name of the file and whatever the context, whatever the contents of the file are before the model runs, basically just some random text. And we basically restrict that this place can only contain tuple types. So Snakes is able to do this, so you can restrict the type of tuples that is possible. And because these are colored Petri-nets, this can be basically any data type in Python, and the various types are available like string, integer, and you can even create your custom data types for putting into places. For more information, you should look up the documentation of Snakes itself. We also have to try to simulate programs who want to read and write to the file. And this we do by just like tiny numbers. So we're just using integers to represent different programs. We're not going to put anything complicated like the contents of the instructions of the program in memory, stuff like this. Obviously this is relevant, but not that relevant for this simulation. And we also create some other places. For example, in this place, we're not choosing to restrict the tuples, but theoretically we could also add the tuple here. But this we will explain a bit later. And in general, you can also add transitions in a similar way. So for example, the transition read file is something that just that has no guard expressions, whereas the write file transition here has an expression that ensures that whatever combination of PIDs and files exists. So basically it makes sure that you're writing to the same file that it read from. It's just a simple thing here, because technically our simulation allows you to simulate multiple files existing at the same time, multiple processes, and like you could have different processes reading from different files and so on and so forth. And in general, the way that this Petri-net model is structured is that we first, so randomly one program is selected from this place because there are two tokens here available, as one token here available. A file is selected and a PID is selected. And to indicate that a program has read the contents of a file, we just transfer this here. Basically, what this means is, so the file doesn't actually leave the file system, but the program essentially copies the contents of the file into its memory, and this is basically what this place represents, the state of the system where a program has read the contents of the file into the memory. If we execute the transition for once, basically you can see this. I've already done the execution. So you can see, for example, here that program 1, when this transition is executed, has read file 1 and has some random text. So basically, it's read the file and now it's waiting to write something. So now this transition is now enabled because this file exists in the file system still. And also there is some program that has read the file, and then maybe the writing will take place now. But the thing is that both this transition and this transition are currently enabled because there is still another program ready to read the file. There is still a file in the file system, while also there's a program that's still currently read. So you really cannot tell which transition is going to fire next. So let's actually see what happens. Well, it seems like in this case, because it's a random choice between the two, it seems like program 1 has written to the file, and the way that we are indicating that the file has changed is you see that we are simply appending the file contents and basically the PID of the program that's read as an indication that program 1 has written to the file, seemingly before program 2. And if we see, then the next thing that happens is program 2 reads from the file and then simultaneously also writes. And at this point in time, there are no enabled transitions, which is why the simulation is going to stop. As you see here, there's no program that has a read file. There's no program that wants to read any file. So that's where our simulation ends. This is one possible execution path, but if we execute it a couple more times, we will see something different. So the initial case is always the same, that because this is how the CPN works, the initial state is always set based on our initial tokens that we set here. But sometimes you might have something different happening. Okay, this time the second step is still the same. Program 1 is always the first one to get selected to read. Let's look at the third one. Oh, it seems like this time also the same thing happened. Let's try to execute it one more time to get some kind of a different result. There is something different this time. So this time, same as before, program 1 reads the file first, but before program 1 is able to read from this file, it seems like, let me just zoom in to a proper reasonable amount. Yes, it seems like program 2 also reads this file. Basically because we have nothing preventing program 2 to also read the file, even though program 1 hasn't written back to the file yet. So we have no locking mechanism that generally operating systems have to prevent this sort of synchronous behavior when it comes to especially writing and reading to files. This is a very classical computer science issue that can happen. And if we look at the consequences of this, it seems that it seems that, well, first program 2 writes to the file, and then program 1 writes to the file. It seems basically that whatever contents that program 2 wrote is simply overwritten by program 1, which is not really what you want. What you want is that both programs read the most latest version, and depending on which program is writing to the file first, needs to be able to written the program that's read the file first should write the file before the other program reads from the file simultaneously or consecutively. This is the problem that we have here. So if this is executing correctly, what you actually should really see is that both files are you can see both files inside of the random text that is in the file after execution. So your end state should always look like both files having written to the file, and they know, and they basically are always working with the up-to-date version of the file. So your first assignment is basically to fix this problem and fix this PetriNet model. You can do whatever type of locking mechanism that you like, as long as you are using these libraries that we have provided in the package. Yes, that basically concludes this basic tutorial on how to use these PetriNet library for our exercise.